Alright, so here's the video for Chapter 3, which is all about radiation. Of course, it turns out that there's many forms of light. When we start talking about light, generally we talk when the average person says light, they mean visible light. Of course, there's a lot of other forms of radiation, infrared, ultraviolet, and so forth. So we're actually going to talk about that today. What's really important about this, we're going to go into this in more detail here, but the stars and most of the planets are so far away. The stars are really far away. That we could never hope to go there within our own lifetimes, right? I mean, literally, if you take the fastest thing there is in the universe, light, the speed of light, which is, if you recall, 3 times 10 to the 8th meters per second. It literally takes years, like to go to the nearest star to the sun, which is a star called Proxima Centauri. It takes more than 4 years for the fastest thing in the universe to travel there. And of course, so that means, when the light that we see from Proxima Centauri is more than 4 years old. Anyhow, that's stuff we talked about in Chapter 2. But there's lots of information in light, and so that's really how we get our information about the rest of the universe. Most of the information comes from radiation or light. All right, so let's get into this. These are the different topics we're going to talk about. Information from the sky, what a wave is, the entire electromagnetic spectrum from gamma rays to radio. We'll talk about those. Thermal radiation, the fact that when things are hot, they give off a specific type of radiation, also known as black body radiation. And when an object is hot and emitting light, we can actually tell the temperature using the Kelvin scale, the absolute scale. We'll talk about that. And then, of course, what's called the Doppler effect, which is, you might have heard of this when they talk about a Doppler radar, for example. What the Doppler effect is, it gives you directional information, and it also gives you speed, the speed that something is traveling, so whether something is moving towards you or away from you. All right, so we'll talk about that. All right, so here we go. Let's see. I guess I should have done this already. So there we go. All right. So as we said, as I just mentioned, the light from the stars like this, of course, is what's called the Andromeda Galaxy. It's the nearest large galaxy to the Milky Way, which is it actually is about twice as big as our own galaxy. Anyhow, the light from that has traveled 2.5 million years to reach our telescopes, or to reach our eyes. That's actually one object that you can see if you know where to look in the constellation Andromeda, obviously. Anyhow, you can actually see it in the night sky. It's a very faint, kind of a hazy little patch of sky. Anyhow, there's incredible amounts of information that's actually in the radiation itself, and we learned how to decipher that information over the last about 150 years. All right, so we're going to talk about that and what we can find out from the light. All right, so the first thing is what is a wave? Okay, so we could be talking about water waves or sound waves or light waves. So light, in some sense, is a wave. Why I say that is because in the field of what's called quantum mechanics, it turns out that light is also a particle. It acts like a particle as well as a wave. All right, so right now we're just going to talk about the wave nature, and so the distance between successive parts of the wave, like from crest to crest, or from trough to trough, it doesn't matter. As long as one complete wave one complete oscillation has taken place. The distance between that is called the wavelength, and the symbol that we usually use is lowercase lambda, the Greek letter lambda. All right, so that's one of the aspects of the wave. There's another idea called the amplitude of the wave, and that's basically the distance from the center of the wave to either the top of the wave or from the center of the wave to the bottom of the wave. All right, so that's in some sense it has to do with how strong a signal is its amplitude. Another quantity that we use quite often is what's called the frequency, and the frequency has to do with this. Well, actually, let me back up a little bit. What the other thing that we talk about is the period. Okay, so the period is when one of these one cycle of the wave, so one complete cycle, one complete oscillation of the wave passes some point, some arbitrary point in a given amount of time. And so that's what's called the period. And then the reciprocal of the period, 1 over the period, is what's known as the frequency. And all right, so we'll talk about that a little bit more. All right, so again, here's water waves, for example. You throw a rock into a nice calm pond, and the ripples, of course, are really what represents the wave, and the distance between each ripple is what's called the wavelength. And so the water here is what's moving up and down. That's what's where the energy is going. It's causing, if there were more energy, if there were greater amplitude, the water waves would go up and down even higher. All right, or if there's less energy, they would go up and down lower. All right, so really, what a wave is all about is energy being moved from place to place. It's one way that energy can move. Okay, is through wave travel. All right, so as I said here, the frequency is the number of waves. It doesn't have to be the crest. It's any part of the wave. Usually it's the crest that we talk about because it's just easy to sit there and look at, oh, okay, well this is the from this point to this point or something like that, but again, it's any complete wavelength that passes by. So the number of complete waves, complete oscillations that pass by per second is what we call the frequency. All right. The period is just simply the time it takes one complete oscillation to complete itself. So that's what the period is. And so there, as I said, there's a relationship between the period and the frequency. So the period is 1 over the frequency, and also, of course, the reciprocal of this is true. The frequency is simply 1 over the period. All right. There's not a lot of. I should mention this now that there's not a lot of math that we're going to do in this course. However, you do have to be familiar at least with some of these terms without very little actually using these things in calculations. Using them in calculations will be more what we do in the labs, right? And which we'll get to shortly. All right, so oops, I went a little too far here. All right, so the wavelength, of course, is the distance between successive parts of the wave, not just the crests. The velocity is simply the wavelength, right, divided by the period. And of course, since the period is you know, 1 over the frequency, then you could also write this as the velocity is equal to the wavelength times the frequency. And so that's in fact that's a lot of times that's how we talk about the how the velocity is related to the frequency and the wavelength. All right, so that's that. All right, a long time ago, humans have been doing this for a good more than 400 years. Humans noticed that when you pass light through a prism, the light breaks up into all the colors of the rainbow, and so that turns out to be a really important idea. It was actually Isaac Newton. So we talked a little bit about the different contributions of different scientists. Newton actually proved that white light is composed of all the colors of the rainbow. And basically what he did is he took a prism, broke the light into all its component colors, and then took another prism and showed that all these colors would combine again into white light. So that's what he did. Let me just mention in modern times we really don't use prisms very much anymore. Prisms are they're expensive and they're heavy. In most telescopes nowadays, we use what's called diffraction grating. It's very very inexpensive. It's basically little pieces of plastic with a whole bunch of lines. Manufactured. Well, they're actually organic molecules that line up very very in a very fine way, in a very accurate way. And anyhow, all right. So this is the what's called the visible spectrum, right, from purple to red. And there's several things that I wanted to mention about that. Whoops, sorry. There's several things I wanted to talk about that. So there's some trends here. The purple light has more energy, and also the frequency is higher. So the red light has less energy, and the frequency is lower. And the opposite is true about the wavelength, right? The wavelength of purple light or violet light is shorter than the wavelength of red light, and actually the trend goes this way, right? As if you had green light, the green light would have a longer wavelength than the purple light, and same thing, the yellow light would have a longer wavelength than green light, and so forth. So red, the visible part of the spectrum that is the deepest red that we can have, that the humans with our eyes can detect is actually normally astronomers talk about this in terms of wavelength, and so red light, the deepest red that the human eye can see is about 700 nanometers, and the deepest purple light that the human eye can see is about 400 nanometers. So that little range, a nanometer, of course, just to remind everybody, is that would be like 700 times 10 to the minus ninth times 10 to the minus ninth meter. So that's a really small, wavelength. That's extremely small. So this is what's called the visible part of the spectrum. And notice there are other parts of the spectrum, right? And in fact, it was an astronomer who first determined. It was Herschel, the guy who found the planet Uranus back in the 1700s. That there was this region here called the infrared. All right, I'll talk about that more in the next video.